Hello everyone, this is a discussion on motion in one dimension as well as a discussion on kinematic equations, which will nicely summarize our discussion on motion in one dimension. And then we'll do an example thereafter using such set equations. Now there are three really main components we need to discuss when discussing motion in one dimension. And those are displacement, velocity, and acceleration, which we'll discuss in the next board. But displacement is the overall change in position, or otherwise known as distance traveled. And really this is the change in distance. Can't emphasize that enough. So we describe that as being delta x, which is change in distance. So anytime you see a triangle, this is change in. Change in whatever. So delta x is change in x, delta t is change in t. Okay, good. Now this triangle is the Greek letter delta, so we say delta instead of triangle, for instance. Now the subscript F stands for final, and the subscript I stands for initial. So this is the final value minus the initial value. So a few things kind of come to mind here. So let me write that here in red. Delta x can be 0 or even negative. It is totally possible. Now, if it is 0, it doesn't mean you didn't move at all. It just means that your displacement is 0. What does that mean? Well, that means that you may have moved, but you're back where you started. So if you, let's say, walk a certain distance and then walk back that distance, your overall change in distance is 0 because you're back where you started. That, I think, makes sense. Now, as far as negative goes, well, it means you actually were pushed back further than where you started. So you're actually moving backwards overall instead of forwards. So that would entail, well, let's just kind of imagine we have a point of reference. So if I'm moving toward our point of reference, or I guess it would be away from our point of reference, then we would have a positive displacement. But if we move back towards our point of reference, then we'd actually have a negative displacement, which I know sounds a little funny because I haven't really introduced point of reference yet. But we'll get to that when we actually see some solid examples. But for right now, let me just say that delta x can be 0 or negative, and that it is not the distance, but it's the difference in your first distance, and your final distance away from a certain point of reference. So xi is the initial distance from something. So it has to be distance from something. In fact, you know what? I can give a nice example here. Just do that in red so it kind of stands out. So let's imagine that, it's going to be a little dumb of an example, but let's imagine we are next to, I don't know, let's say a door. So let's say we're in a room or outside of a room, outside of a building, something like that. And here we have a door, and we are, let's say, 5 feet away from the door, and then we move so that we are now 12 feet away from the door. A little longer. There we go. So the door in this case is our point of reference, kind of like I was mentioning earlier, but we'll see more of that in later examples as well. Our initial distance, so this is our initial position, this is our final position. So xi is going to be our initial distance from the door, which is 5. xf will be our final distance from the door, which is 12. So that means that our change in distance, our displacement in other words, is 12 minus 5, which is 7, and of course it's in feet because the unit of measurement here was feet. Good. So notice really what that means is we moved forward 7 feet. So that's a way to think of what displacement is doing, your overall change. But again, if we move toward our point of reference, it would be negative. So if we started 5 feet away from the door, but then ended 3 feet away from the door, then we moved 2 feet towards the door, so that'll be a negative 2 displacement, which makes sense because that would be then final, which would be 3 minus 5. 3 minus 5 would be negative 2 for the displacement in that case. So again, something to think about, but I think I've said enough there for displacement. Now, velocity is a little different. There are actually two types. There's average and instantaneous. Instantaneous is more for a kind of calculus-based physics, which we won't really be discussing. But if you have taken calculus before, then you have definitely seen limits And if this doesn't look familiar, this is really the definition of what is called derivative. So derivatives and velocities are very, very much entangled. In fact, a calculus-based physics class would be obviously a little more advanced because you have more tools to use, and derivatives would come up quite a bit. But I'm not going to really talk about that too much. I'm just kind of mentioning it right now. Now, as far as average velocity goes, that's the displacement traveled divided by the total time elapsed. So here, that's delta x, which we know now is xf minus xi, over delta t. T is the time elapsed. So delta, again, means change in. So, much like we have for delta x, delta t will be tf minus ti. Perfect. Now, very often we're not actually given the initial and final times. We're just given the actual change in time. Again, it depends on the problem, but it's nice to know that that's how this kind of expands. And instantaneous velocity would be velocity not over a elapsed time, but at an instant, meaning there's no really change in time at all. So notice we have this limiting factor that the change in time, so there should be a delta t here. So the change in time will be approaching 0. Now what that exactly means is that it's, well, I have really no other way of saying it in words, but at an instant. Now what is an instant? An instant isn't a second, it's not a millisecond, it's smaller. It's the smallest, I guess, measurement of time you can kind of think of. So again, the more you think of it, the more it kind of boggles the mind. But at an instant just refers to, again, the smallest kind of interval in time. So that's what we're kind of discussing there. So it's a limiting process, and if you know derivatives, it'll be easier to find instantaneous velocity. But as it turns out, we won't really be discussing instantaneous velocity too much in this class. We'll be discussing more average velocities, and I guess that's really it. But now we'll discuss acceleration, and we'll see that what velocity is to displacement is exactly what acceleration is to velocity. So let's take a look at that right now. All right, so before moving on to acceleration, actually, one thing I kind of left out was speed. Now, speed opposed to velocity is really just the absolute value of velocity. It is really the magnitude of velocity. So average speed would be the magnitude of average velocity. Instantaneous speed would be the magnitude of instantaneous velocity. And what this actually implies is that, well, magnitude, what's magnitude? Magnitude is, well, it is actually something associated with vectors. So what this implies is that velocity is actually a vector quantity. So that is certainly true. Velocity is a vector, whereas speed is the magnitude of that vector. A magnitude. So in other words, it's a pure number. Whereas velocity actually has direction and magnitude, which makes sense because, again, we're dealing only in one dimension motion here, motion in one dimension, and velocity could be negative because delta x could be negative. Now the change in time will always be positive because time always goes on and gets greater and greater. But the way we define displacement can get smaller and smaller and even negative. So if you're dividing negative number by a positive distance in time, or I guess I should say change in time, really, well then what you end up getting is a possible negative velocity. Now what would it mean for a velocity to be negative? It would mean that you're going that speed in the opposite direction. So what one dimension really means is we're traveling on a line. Traveling on a surface is a really nice way of thinking of it. So you can imagine, let's say, a car or a plane moving along this line. So either the car can go this way or it can go backwards. So let's say a car of, let's say velocity positive 50 miles per hour would be going in one direction, usually seen as in the positive x direction, whereas if it's going the opposite way, then it would have a negative velocity if it was heading in the other direction. Okay, but notice both of these different things, so there's kind of two cars in this case. So let me just draw it like this. You have one car going one way and one car going the other way. So both of these cars, though they have different directions, so they have different velocities, actually have the same speed because the magnitude, which is just the absolute value actually of the velocity in this case, it'll just be 50. Okay, anyways, moving on. Acceleration is the rate at which velocity changes. Now, rate really is what velocity described. So the rate at which something changes is its change in that quantity divided by change in time. So notice the rate at which, I guess you could say distance changes is the change in distance, which is displacement, divided by change in time. And that describes velocity. So velocity is the change in distance, the rate at which distance changes, I should say, and acceleration is the rate at which velocity changes. So notice it's exactly our definition we had for velocity, but now instead of dividing x by 2, we're dividing v by t. So a bar we'll use to be the average. So the average acceleration will just be the change in velocity, so vf minus vi, over the change in time, which is of course tf minus ti. And a without the bar on top, much like v without the bar on top we saw previously, was the instantaneous velocity. So this would be the instantaneous acceleration, where we're having the limit of these average velocities as the time is getting smaller and smaller so that there's no time at all. It's within one instant. Good. So now I have an example here, and it's a kind of interesting example because it's something that we've kind of probably seen a lot in everyday life. So we want to find the average acceleration of a car going from 0 miles per hour to 60 miles per hour in 3 seconds. Now it's pretty fast, going from 0 to 60 in 3 seconds, but what's hardly discussed when you read these kinds of things or see, these kinds of things in action is the acceleration. What is the acceleration? So there are different units of acceleration. Of course, if we have SI, the standard international units for distance and time, of course, if you don't recall, were meters in seconds, so that would be in meters per second squared. Now where the square comes from, we'll kind of see, kind of think of it like this. So again, in SI, velocity would be measured in meters per second. And in SI, time would be measured in seconds. So the unit for acceleration would be meters over second over second. So actually what you could do is if you just take this formula as granted without doing any unit change, you get a weird unit. You get miles per hour per second, which you could discuss. You could actually use that unit, but it's kind of a weird unit. It's not a standard unit. Feet per second is more standard. Of course, the international standard would be meters per second squared. And again, why it's second squared is because we're dividing second by second. So in fact, if you want, you can think of this as s over 1. And if you're looking at the units, the unit here will be m over s, so meters over second, times the reciprocal of s over 1, which is 1 over s, which is m over s squared. So this is a little calculation in the unit. So the unit of acceleration would be the distance unit divided by the time unit squared, so long as they're all in the same unit. Now in this case, our time unit for these speeds here are in hours, not in seconds. So we have to do some unit conversion. In fact, here I specifically say to use feet per second squared. So with that said, let's convert each of these to feet per second. Now 0 miles per hour is still going to be 0 feet per second, but 60 won't be. Let's actually calculate 60 using our good old-fashioned conversion table. So it's 60 miles over 1 hour. We want to convert that to feet per second. So remember how that goes. We want to get rid of miles. We want to introduce feet. There's 5,280 feet in 1 mile. That'll cancel miles out. Now we're in feet, but we want to convert hours to seconds. So since we want to cancel hours and it's in the bottom, we want hours to be on top here. And in 1 hour, there is 60 times 60, which is 3600 seconds. So here the hours cancel, and our total overall unit is feet per second. So now 60 miles per hour is whatever 60 times this number divided by this number is. So let me calculate that real quick. And I actually got a really clean number. So this total results in 88 feet per second. So this is our final speed. I say speed because we're moving only in one direction here, but really it's velocity. So we have that our initial velocity is 0 feet per second, and our final velocity is 60 miles per hour, which in feet per second is 88 feet per second. So really what we want to do to find our average acceleration is use this equation here. I have a little bit of space over here, and it's not really too much work. So let's see if we can cook this up over here. I have A bar is equal to delta V divided by delta T. Now we know delta T, let me kind of border this off. Delta T is given, that's the change in time. The change in time is 30 seconds. So I'll just write 3. Now the change of velocity is going to be the final velocity, which is 88, minus the initial velocity, which is of course 0. Great. So now in total we have 88 divided by 3, which we can just use our calculator, of course. And we'll get approximately, let's see. So I got 29.3, let me write it down here. 29.3, now it's going to be feet per second squared. And again, why it's second squared is because it's an acceleration. An acceleration will always have the time unit squared because it's feet per second per second. So what this really means, if you want to kind of think of it in kind of a different way, is that after every second passes, the velocity will increase by 29.3 feet per second. So after 1 second, it increases from 0 to 29.3 feet per second. After another second passes, it increases by yet another, the velocity will increase by another 29.3 feet per second. And after a third second passes, it'll finally increase by another 29.3 feet per second. And in total, it'll have 88 feet per second, which is equivalent to 60 miles per hour. Awesome. Now, that's really all I wanted to say as far as motion in one dimension goes. Now we're going to take a look at what are called kinematics, and it's a very particular case involving this setup I've just given you, and we'll be taking a look at really, really nice particular equations that we'll be using throughout the entire class. Right, so now in order to derive the kinematic equations, we need to assume a few things and then also relabel a few things. In fact, we're only really going to make one assumption here. So our one assumption is that we want to assume that acceleration is constant, so our acceleration is not changing. Okay, so what that means is that the average acceleration will be equal to actually the instantaneous acceleration. Then I want to relabel delta t as just t, final velocity as v, and initial velocity as v naught. Or you can say v sub 0 or v 0, but I say v naught. And a few things will come out. In fact, well, we know that the acceleration a, so from this right away we'll see the following. We know that a is equal to delta v over delta t, but delta t is just t. Delta v is v final minus v initial, which with our new labeling is v minus v naught. If we multiply both sides by t, looking at the extreme right and extreme left, we'll get that at is equal to v minus v naught. And then if we add v naught to the other side and then flip the equality, we get v is equal to v naught plus at, and this is our first kinematic equation. And the next kinematic equation, which to be quite honest is very often not considered, is v bar, the average velocity, is just the initial velocity added to the final velocity divided by 2. So it's actually that the average velocity, which is of course delta x over delta t, which we relabel as t, is equal to, well, the actual arithmetic mean, or average, you can say, of the initial and final velocity. And this, of course, is due to the fact that acceleration is constant here, meaning that the velocity is increasing by a constant rate. So it's something you can think about a little bit, but this is indeed true, and it's very often not really considered too much as an actual equation, but I'll actually write it as such. So let me do this. Allow me to solve for delta x by multiplying both sides by t and bring this 2 as a 1/2 out in front. So we'll get delta x is equal to 1/2 times the quantity v naught plus v times t. So it ends up not being the most useful. Let me actually put this outside of the box. but it ends up not actually being the most useful kinematic equation, but I will indeed call it a kinematic equation. And in fact, it will allow us to get to the next kinematic equation I want to talk about. And the next one I want to talk about will actually not involve final velocity. So what I'm going to do is I'm going to write this as a v equals v naught plus at and substitute it into the second equation. By the way, let me kind of move this a little bit so we can see what I've written there. So if we substitute that in here, I'm trying to see if there's a better spot for me to, I guess that's fine. So I'll substitute that in here. So now we'll get a new equation. We'll get delta x is equal to 1/2 times the quantity v naught plus v, but we know v is equal to v naught plus at from our first kinematic equation, and then this is times t. Now we don't really need parentheses here. I'm just kind of doing that to emphasize where it came from. That replaced v in the second equation. Now of course these two combine to 2v naught, and we can distribute this into here in parentheses. So we'll get 1/2 times the quantity 2v naught t plus at squared, and now distributing the 1/2 will give us the following. It will give us delta x is equal to 1/2 times 2 is just 1, so that's v naught t plus 1/2 at squared, and that is our third kinematic equation. And now finally I'll be just doing one more. That's of course the final and fourth kinematic equation, which omits time. So each of these are missing something. This is missing delta x, this is missing acceleration, this is missing final velocity, the next one will not have time. It'll not have t, it'll be missing t. So how am I going to get that? Well, I guess what we can do is we can solve for t in one of these, and in fact, you know what? Maybe we can do that here. I guess we can solve for t in this equation. Well, that's fine. So from the first equation, we know this. We know a is equal to v minus v naught over t. If we do a swap, remember that from our discussion in trigonometry, we get that t is equal to v naught, or v minus v naught over a. Very good. And substitute that now into equation 2. I think that'll be enough to actually get what I want to get here. It's going to look a little weird, but let's see if we can plug that in. So we're plugging t equals v minus v naught over a into the second equation. Our second equation now becomes the following. It becomes delta x is equal to 1/2 v naught plus v times t. But t, according to this, is equal to v minus v naught over t. Oh, sorry, no, d over a. There we go, over a. All right, so a few nice things happen. The first nice thing that happens is that, of course, we can write this as over 1, so we multiply straight across. And I'm going to rearrange the order here. Instead of writing v naught plus v, I'll write v plus v naught, just so I kind of have the recognition that this multiplication of these two quantities on top really is a difference of squares from algebra. So it's going to be v squared minus v naught squared. We have the 1/2 in front. Altogether, we get the following. We get that this is equal to all over 2a v squared minus v naught squared. And then finally, multiplying both sides by 2a to this extreme left side over here will give us v squared minus v naught squared is equal to 2a delta x. But then if we add this to that side, maybe this will look a little better if we just keep it like this. So multiply 2a to the left, we get 2a delta x. That's fine. And then adding v naught squared and then reversing the equality gives us finally our last and final kinematic equation, which will be v squared is equal to v naught squared. That will be plus 2a delta x finally. Now, I don't know if we exactly have time, because this video is kind of getting a little long, to do an example using each one of these, but I'm going to do 2 examples only. One will be a scenario where we have kind of a horizontal surface. Then we'll be doing another scenario which is in a vertical dimension, which is known as freefall. And that'll incorporate gravity, which will be nice to introduce that now. And yeah, let's just not waste any time, and let's take a look at that right now. Okay, so this problem obviously seems like a little bit of a doozy. I've written the kinematic equations over here. So what I want to do is I want to read the question, try to draw a picture, label a few things, and then see what kinematic equation is applicable to solve the problem. So let's read. A jetliner lands at a speed of, well, that's really knowing scientific notation. That's moving that decimal to the right twice. That's really 160 miles per hour. And decelerates at a rate of 10 miles per hour per second, which again is that weird unit we kind of discussed earlier, which is, again, it's doable, but it's an acceleration. It's a deceleration, but we'll talk about that shortly. If the plane travels at a constant speed of 160 miles per hour for 1 second after landing before, there should be an E there, sorry about that, applying brakes, what is the total displacement of the aircraft between touchdown on the runway and coming to rest? So here's what I'm seeing. So we have this runway, and there's kind of these like timestamps. There's 3 different timestamps. So we have the plane being, let's say, here. I'm going to attempt to draw a plane, but it's fine. So something like that. There we go. So we have the plane here, and that's the, again, this is the initial landing. And we'll continue for a certain amount of distance, traveling this constant speed of 160 miles per hour. And then over here, some place along the line. So imagine something like that. We end up at the point where we actually start braking. So this is where we apply brakes. And then finally, the plane will be over here, and this is finally where we land. In other words, where we stop moving. So I'm not trying to draw the best type of drawing here, of course. We don't really even need the drawing, we just know that there are these 3 different timestamps. So where we land, that's where we're on ground, so now we're in 1 dimension. Of course, before that, it'd be a 2-dimensional problem because we have vertical and horizontal motion simultaneously. But that's a discussion for a later time. We have these 3 timestamps once it hits ground, and that is landing, applying brakes, and then finally at rest. So there's kind of these 3 themes going on, and our total goal is to find delta x, to find the displacement. So there's kind of these 2 problems really. So here we'll have an initial velocity. Our initial velocity is going to be 160 miles per hour. And our final velocity will actually also be 160 miles per hour because we're going at a constant velocity. So our velocity is not changing. That makes a lot of sense. Good. And now with all of these problems, we're assuming our acceleration is constant. And by the way, here, if our velocity is not changing, it's a little weird to think of, but let me just kind of try to make sense of this. If your velocity is not changing and your velocity stays the same, that means your acceleration must be 0. Because acceleration is the rate at which velocity changes. And if the velocity is not changing, then there was no acceleration. So it's coasting, it's staying the same speed. No acceleration was applied. And then at this point, so I guess from here we can find delta x. I was going to jump to this part of the problem, but again, I said there are kind of these 2 problems that are coinciding. So maybe we can just make use of this. So we have delta x, we have v naught, we have v, and we have an acceleration. So which of these is applicable? So we have delta x, v naught, v, and a. Now, in my experience, the best thing to do is not to look at which kinematic equation involves each of the 4 things we have involved here, but instead to actually look at what's missing. So what we don't have here are our variables. So notice our variables, if you kind of write them all down as one list, we have v naught, v, a, t, and delta x. So there are these 5 variables total in all of the kinematic equations. And notice here we have t missing. Time is not not given here. So with that being said, well, which of these do not have t? That's easier to look at is 4. So I'm going to use equation 4 with this part of the problem, which I'll write over here. So according to kinematic equation number 4, we have v squared, which is 160, equals v naught squared, which is also 160 in this case, plus 2a delta x. But you know what? This actually doesn't really do us any good. Why does it not do us any good? Doesn't do us any good because since a is 0, we just go 160 squared is equal to 160 squared, which is super, super, super unfortunate. The kind of good news, though, is can we find time? I think we actually can find time. I'm trying to think. We want to find delta x. So 4 ends up being actual bogus because a is 0, so that ends up going away. But in fact, what that really does is if you set a to be 0, a lot of these start to make a little more sense. So you can actually find t. So if you look at equation 3 now, so I know that I give you a really good idea there, but in this particular instance, it doesn't really help us too much. But if we use equation 3 is kind of like this, this middleman, so to speak, because using equation 3, we get the delta x is equal to v naught, which we know is 160, times t, plus 1/2 a t squared, but since a is 0, that part goes away. And that combined with equation, I guess we can use equation 2, will actually give us the same thing. So we know delta x and t are one and the same. But actually we are given time here. We're given time as 1 second. So I started labeling things, but I didn't really read through everything. So that's actually good. So we actually do have time in this case. Because in this particular spot here, we have that t is 1. T is 1 second. Whew, nice. There's a little bit of a problem. And the problem, of course, is that second is not the same as hours. They're not in the same unit. So we had to change things a little bit. I'm trying to think how we should change things. It may be better to write this. No. I'm trying to think. If we wrote this in hours, it's going to be really, really small. If we wrote this in seconds, it's going to be really, really large. In fact, what this is kind of telling me is to convert everything into feet. So you know what? This example's taking a little longer than I'd like it to. So here's what I'm going to do. I'm going to erase this. I'm going to write this above, and then we're going to have more space to work, and we'll finish it rather quickly, actually. All right, so I've moved everything up here. I kind of took away the stupid drawings, so it's kind of cleaner to look at, but we at least have the visualization from before as far as what's happening visually. And I have the same labeling. I haven't added anything new. And I've decided that what I'm going to do is I'm going to work with feet per second. Now, we could use meters per second and stick with the standard international units, which I think is actually a good habit. But the reason why I want to use feet per second is because it's a smoother conversion. We actually did this before. So if you have 160 miles per hour using a conversion table, we want to get rid of miles, introduce feet, so that's 5 to 80 over 1, and then miles are gone, feet are now introduced. And now we want to get rid of hours and introduce seconds. And we know there's 300, or 3,000, I should say, 600 seconds in 1 hour. And the hours cancel, so now our unit is feet per second. So this is nice because now we can say 160 miles per hour in feet per second is really just multiplying by 5280 and dividing by 360. So I actually did that already, and I ended up getting 234.7 if you round. So it's 234.7, and that's feet per second. And by the way, the reason why I didn't want to go miles per second, because the number gets really, really, really large. In fact, I'm sorry, it'll get actually really, really small, because we'll be dividing by this to introduce seconds, but we wouldn't have this to balance it out. So 160 divided by 3600 would be point something. In fact, let me just kind of calculate it real quick to tell you. It'd be 0.044, which is kind of a little not really balanced of a number. this I think is better. If you're dealing with either really, really, really small numbers or really, really, really large numbers, the calculation can get out of hand, and you have to stay very, very accurate to get even a realistic answer. So something to kind of keep in mind. But now we've changed these, so let me kind of relabel those here. So these 160 miles per hour now become 234.7 feet per second, which I think is a little more manageable, because now everything's in the correct units. So with that being said, I'm going to erase the work of our conversion here, and I'm going to apply the correct kinematic equation. And now we actually know that the correct one to use is equation 3, because that involves delta x, t, v naught, and v. So in total, what we'll actually end up getting is that delta x, so using equation 3, equation 3 is this one. So when a is 0, that goes away, so we get delta x is equal to v naught t. In fact, even if we use 2 in this case, I pointed to 2 when I meant to point to 3, it would be the same thing, because since v naught is equal to v, you get double one of them, dividing by 2 is just going to be v naught times t, which is the same thing that 3 amounts to when a is 0. So in other words, we get delta x is equal to v naught, which is 234.7, times t, which is 1. So notice they're both in seconds, so we actually end up getting the delta x in this case is 234.7 feet. Nice. So we actually know the answer here, so let me write this in red. 234.7 feet, which I think makes a lot of sense because, again, since 1 second has passed and we're traveling 234.7 feet per second, then we've achieved that many feet. Okay, good. So now, what does rest mean? Well, notice here we're changing our velocities. Well, our velocity didn't change here. But once we start decelerating, our velocity is going to slow down because decelerating means to decrease your velocity. And being at rest means your velocity is 0. And I want to use feet per second here. Now I'm going to relabel things because I'm now done with the first part of this problem. So I'm going to relabel accordingly. The final velocity in the first part is now the initial velocity for the second part of the problem, because we're starting now at this velocity and ending up at this velocity. So that should make a lot of sense. Now we know that our acceleration is a deceleration. Here our, like this, I guess. Here our deceleration was, it was given to be 10 miles per hour per second. And we can convert that into feet per second squared. But of course, it was a deceleration, so it's actually a negative acceleration. So that's something to note. And the reason there is because our acceleration is decreasing by this amount of miles per hour every 10 seconds. So in fact, I wonder if maybe we could keep it in that unit and see if we can get something kind of better there. I think that actually sounds a little better because we can find exactly how much time passes, and then from there we can use that to find delta x. But notice from our labeling here, we want to find delta x. We know v naught, we know v, and we know a. What we have missing is t. And the one that does not have t is equation 4, of course. And none of these are 0, so we don't get any bogus situation we had before, which was good practice. It was bad that it happened, but in some sense it's kind of good practice that we saw how to handle that scenario when things don't quite go our way. So let me just kind of think for a second. So if this is, I don't think it's going to quite work out if we keep this unit. I was kind of thinking it's kind of nice that if we kept the unit, we can calculate the time nicely, because if our original unit was 160 miles per hour, to get to 0, if you're decreasing 10 miles per hour every second, then that means that 16 seconds would have to pass, but that means we actually found time. So in fact, we could use time in seconds to find delta x now in this unit, but that sounds like a little much. So just so I'm not kind of confusing us too much, I'm going to convert this into our unit now, feet per second squared. So I need to find out what 10 miles per hour is in feet per second. So we know that 10 miles per hour, according to the calculation we did previously, is whatever 10 times 5280 over 3600 is. I notice there's a cancellation of zeros here. So we just end up getting 5280 divided by 3600, which is a pretty quick calculation. I got 14.7. So this is about 14.7 feet per second. So that means we're decreasing by 14.7 feet per second every second. So our deceleration now, we write in red, is this number, but it's negative because of deceleration. It's negative 14.7 feet per second, or feet per second squared. Great. So now erasing the conversion work. Let's see if we can figure out, again, which kinematic equation to use. We have V, we have V naught, delta X, so we want to find, and we have A. So the only one that does not involve T and involves these four is, of course, equation 4. We separate these. So by equation 4, we have V squared, which is 0. So let me just write 0 squared is equal to V naught squared, which is 234.7 squared, plus 2 times A, which is a negative 14.7 times delta X. So notice here, since all of the units line up, the time units are in seconds, the distance units are in feet, I don't really care about writing the unit, and I'll just write the unit after the fact, really. Great. So now I'm going to do some computation here using my calculator, and then we'll solve from there. Right, so using my calculator, I got these values after scoring this number and multiplying this by 2. And now finally, to find delta X, I'm going to subtract this to that side. Or I guess, we can add this to this side. Let's do that better. Let's add 29.4 delta X from the right to the left. At some point, you don't need to write the actual movement of it. That's okay. And now finally, to find delta X, we'll actually just divide by 29.4. Okay, finally, good. So now dividing, we get what for delta X? So we get delta X is approximately, I got 1873.6, and this is delta X in feet. Now this doesn't entirely finish the problem, but it is super, super, super close. So we found out that for the second part of this problem, we found the distance here being 1873.6. That's, of course, in feet. And now finally, all we have to do is find the total distance by adding these values. So if we add this one to this one, I'll just do that real quick here. We actually get a 2108.3. So the total displacement, finally, in feet, will be a 2108.3. And again, since the problem did not specify what unit to have it in, we can actually have it in feet. The book actually has it in meters, and they have 644. And in fact, if you convert this to meters, I guess we could try to do that real quick. So if we convert to miles by dividing by 5280, and then, let's see, we would multiply this by 1.609, and then move the decimal place to the right 3 times. And I get 642, not 644. And the reason why it's off a little bit, it's good to mention this, is of course because we rounded as we went along. And the more you round as you go along, the more off your answer will be and the more accuracy you lose. But it's not that far off. It's off by a few meters. So in fact, I want to say that this is in fact the way I would like you to do a problem like this, let's say on an exam. But maybe that's just me. So like I said, I want to do one more problem. I know the video is getting really long, but I want to do one more problem involving Freefall, and that'll introduce gravity to us. And I want to make it quick. I said this one would be quick, but it's kind of long. But let's take a look at that right now. So now finally for this example that I called Freefall, and it's basically the same type of example we looked at before, only now vertical. So it's still in one dimension. Now, the only thing though that I need to give us, so there's not really much given here, I didn't even write too much of a description, But let me just kind of describe the scenario. So we have a guy on top of a building that's 50 meters. He's throwing a ball up with the initial velocity of 20 meters per second. And the idea is that the ball is going to reach a max height eventually somewhere over here and then fall back down. So we're not worried about any horizontal motion. We're just imagining throwing it up and it going straight down. So just imagine that's the case. So he's throwing it so that it's like right over the edge of the building or something like that. That way there's no horizontal movement at all. Great. Now the good news is that unlike the previous problem, there's no conversion to do. It's in meters per second, it's SI, great. The second thing is not much is given. We're only given a height and an initial velocity. So now I want to introduce something that is gravity. So gravity I'll denote by the letter G, lowercase letter g. And what gravity is actually specifically the acceleration of gravity. And this is on Earth. So different planets have different accelerations of gravity. We'll discuss that maybe later. But the acceleration of gravity actually on Earth is about 9.81 meters per second squared. And well, in feet per second squared, I believe it's like 32, something like that. In fact, most people in books just write 9.8, but it's actually 9.81 to 2 decimal places of accuracy. So I'll use this. So now we want to find these. We want to find the time for the ball to reach max height. We want to find the max height itself. We want to find the time for the ball to return to the original height at which it was thrown. And then we want to find the time the ball will take to reach the ground. So let's see if we can do these just right now. So the time for the ball to reach max height. So the max height will be here. What we kind of notice is that since gravity is going against something moving upward, unless it has like thrust, which this doesn't, then the velocity, initial velocity is going to start at 20, but as we throw it up, gravity is going to decrease because it's decelerating, because we're kind of opposing gravity. Gravity's tending down, you can think of it like that. It's pushing this ball down. Since we're throwing it up with this initial velocity, the velocity will decrease until the velocity is 0 meters per second. So when the velocity is 0 meters per second, we know gravity. We want to find the time for that to happen. So the kinematic equation we're going to be using actually is the first kinematic equation, which is V is equal to V naught plus AT. Now, in our particular case, gravity is always going down. So very often we treat gravity as being a negative acceleration. So I'm going to actually modify this equation like this. V is equal to V naught minus GT. Now this is in a vertical instance when gravity is taken into account, when we're going against gravity. So now, keeping these things in mind, our final velocity is 0, our initial velocity is 20. We know gravity is 9.81, and now we can find time. So subtract 20 to the other side. We get this, or we could have added 9.81 t, but that's okay. And then divide by negative 9.81. And we get that t is about, let's see. So I got about 2.04. And that's of course going to be in seconds because, well, our time unit is in seconds. There's no time conversion here needed. So in fact, I'll write that answer in red and then we'll erase and move on to B. So this is 2.04 seconds. Right, so now for part B, we want to find the maximum height, and we're honestly given really the same things we can use here. So let's do this. Let's take a look at kinematic equations that involve V naught, V, and delta Y. So, well, I want to use delta Y instead of delta X. So that's the modification I'm going to be doing on the kinematic equations. Kind of like how we replaced A with negative G, we're going to be replacing X with Y so that we're kind of more, reminds us more of vertical opposed to horizontal. So the one I'm going to use is delta X is equal to 1/2 V naught plus V times T. But of course I'm going to modify this a bit so that it's delta Y instead of delta X. Now, it's really nice here. We know that V is 20. V is 0. We know that V naught is 20. So this ends up being 1/2 times 20, which is just 10. So since this is 20, 1/2 goes, let me write it above like this. We know 2 goes into 20 10 times. So this in total will be 10 times t. Well, we know t is actually 2.04. So that means delta y will be 20.4, and that's going to be meters. Because, of course, the distance you know is meters here. So now I'm going to box this over here in red, much like I did with part A. So I got 20.4 meters. And now we're going to move on to part C. All right, so now for part C, we know a few things, and the problem has changed a bit because now we're starting here and moving down. So let's see, time for the ball to return to the original height at which it was thrown. Now, we know the time it takes to get to the maximum height, and then we'll actually go from there. So if we start here at this maximum height, then this is now going to be our initial velocity. Okay, so we can forget about this now. Now we're kind of changing the problem because we're in a different part of the problem. And we want to find the time it takes to get to here. And we don't know the actual velocity here. That's fine, we're not asked to find velocity. But we want to find the time it takes for the ball to get back down here to the original height. And we actually know the height, we just found out that's 20.4 meters. So we have, let's see, we have delta y, we have v naught, we have g, and we want to find t. So the equation we're going to use here is delta y is equal to, I believe it's v naught t, and I would say plus at squared, but since a is replaced with negative g, that's going to be minus gt squared. Now, I guess we could use this. We want to find time after all, but I don't know if it's actually the best one to use. You know what? It's actually not that bad because look, since v naught is 0, that goes away. If v naught wasn't 0, we'd actually have to use quadratic formula, which I haven't done in this video, but you can kind of see that we'll get a quadratic in t, and quadratic formula will be applicable there. Now delta y is 20.4. This is 0 minus 9.81 t squared. So just divide by negative 9.81, and yikes. So what's the problem? The problem here is that we'll be dividing by a negative. So when you divide by a negative, your answer will be negative, and then when you square root, we'll have a negative instead of a square root. That doesn't sound very nice. So as it turns out, the max height is 20.4 meters, but our original height, our kind of initial height here, our yi, if you will, would be, let me kind of write it, let me erase this, fine, move it up a bit. So our initial height is 20.4 meters. And here, our final height would be, well, I guess it'd be 50 meters, but if we want to call it 0, to get back to original 0 height, I guess we can do that. You know, it's fine. Let's think of it like this. So in total, the total height is 70.4. That's probably the best way to think of this. So 70.4 meters above the ground, that's the initial height. The final height will be 50 meters. So what that actually tells us is that delta y is what? It's yf minus yi. And notice that's going to be 50 minus 70.4. And what does this tell us? It actually tells us that in this case, since we're going down, our delta y value is actually negative 20.4. So really this is a negative value because we're going down. So a better way of thinking of this is that gravity is actually assisting us here, not going against us. So one way of doing this is actually to make this positive, but it ends up being the same if we make this negative. And I like this better, it kind of makes more sense to me. It's more to think about, but it only reinforces your knowledge, honestly. So now this is good because now that this is negative, negative divided by negative is positive. We don't get that issue we had before, we have a negative inside of the radical. So we'll have t squared is equal to 20.4 divided by 9.81, in which case my calculator is giving me 2.08 if we round. And if we square root to get t by itself, the square root of 2.08, I'm going to leave it as is in my calculator. So I'm going to square root the previous answer to remain super accurate, and I get about 1.44 seconds. So it takes 1.44 seconds for it to come back down. So it comes back down faster than it actually reached its max height. It's kind of interesting. So let's see, the time for the ball to return to original height at which it was thrown. The issue is I don't know if they want us to find the total time from when we threw it or from its maximum height. But I'm just going to write this answer here, 1.44 seconds. And the reason why is because it doesn't take too much effort to just add these A and C results to get the total time it takes from the original throw back to it coming down. And now finally we're going to do D. Right, so now from part C we learned a lot. We learned that this distance should be treated as a negative value when we're going down. So really our delta y in this case is going to be negative 50 meters if we start from here. The only issue I have is that if we start from here, well, we don't know the initial velocity here. We don't know what the velocity is here. We know the velocity here, but then we'd have to use delta y being the total negative 70.4 meters, which I actually prefer. So let's do that instead. So let's say that since the total distance here to here, is 70.4 meters, and we actually have the delta y is equal to negative 70.4 meters, of course, because we're going down. Great. And our initial velocity here is 0. Fantastic. So we have v naught, we have delta y, and we have g. What are we trying to find? We're trying to find t. So we actually have an equation. It's the same equation we just used for c. It's delta y is equal to v naught t minus 1/2 g t squared. And I'm realizing right now I don't think I included that 1/2 there. So this I don't think is entirely correct. So I think we may have to go back on that, which is a little unfortunate, but again, I'm not writing the equations here, which I probably should have. So let's just kind of find this answer here first, and then we'll go back and fix C. But for right now, of course, v naught is 0. So that goes away. Delta y in this case is negative 70.4. Now, since g is 9.81, we can just half 9.81, and we get 4.905. So then dividing both sides by negative 4.905 gives us the t squared is equal to, let's see, so we got 70.4 divided by 4.905, that's 14.35 about. So then square rooting this, we get that t is finally 3.788. It rounds to 7.9. In fact, let's round it to just 3.8. I guess that's fine, 3.78. Sorry if I seem a little indecisive. So 3.78 seconds for it to touch the ground here. Now, how does this? How can we use this to fix our answer for C? So it's kind of unfortunate that I made a mistake there, but that was in our equation. The mathematics was still correct. So what I'm going to do is I'm actually going to go back in my calculation a bit, and in fact, notice that this is the same calculation. The only difference was that with D, our delta y was what? Our delta y was 20.4, not 70.4. So if we do 20.4 divided by not 9.81, but now by half of 9.81, which we know is 4.905, and then square root that answer, we get 2.04. So this is 2.04. Aha. That is something that I was expecting kind of more. I was a little surprised that it took a shorter amount of time to arrive back at where we started. It should be symmetric. And notice it is. So it actually takes the same amount of time going up opposed to going down. Now, the time for the ball to reach the ground, this is from the maximum height. But again, if you want to find from the original throw, you can just add the answer in A to the answer in D to find how long it'll take you from your original throw for it to hit the ground. Now that's a good place to stop the video. No, it's kind of a long one, but there was a lot to discuss here, so I don't see it being rare that people go back to this video to kind of see little details to help you along with the homework. So it's a good video, but it's long. So thanks for watching. I hope you enjoyed. I'll see you in the next videos. See you then.